Okay, the quantum mechanical view of the atom. All right, so just to recap what we've already said in class. One is that the thing that one of the things that quantum mechanics is very concerned about or focused on is the wave function, the Greek letter psi, the wave function. And the wave function is simply the amplitude of the matter wave. So when we talk about, here we're talking about where is the electron? That's what we're trying to figure out. Where is the electron in the atom? And so the wave function is really the amplitude of the electron's wave as it moves in the atom. And so it was thought that if we could figure out the amplitude at any point in time or place, then we would know exactly where the electron is. Okay, so Schrödinger did a whole bunch of work to calculate the wave function. But along comes Maxwell Born, and Born realizes that really we can't find exactly where the electron is. The best that we can find is the probability of it being there. And the probability of where an electron is simply the wave function squared. Okay? So today or in class, you got to meet Dr. Quantum. And Dr. Quantum did the double slit experiment with electrons. Okay? And what we saw was no big deal. When an electron went through a single slit on the back wall, it just made a pattern of a single slit. But when electrons went through a double slit, they behaved like waves. So an individual electron somehow managed to pass through both slits at the same time and interfere with itself. And that is really what moves us into quantum. Like the idea that somehow an electron can be going through both slits at the same time. Okay? And it goes back to the probability here, because when we think of the probability of like the wave function squared, what we're really saying is that the electron is really considered to be in all spots on this wave at any given moment in time. And when Dr. Quantum was talking about by trying to observe exactly what the electron is doing, we're collapsing the wave function. What he's saying is that we're forcing the electron to go to a single spot, even though that isn't where it would normally be. Okay, so we're changing the experiment we're changing the behavior of the electron simply by trying to study the behavior. Okay, and it takes us to Schrödinger's cat, that idea that the cat can be both dead and alive at the same time is the same idea as an electron can be in more than one place at the same time. And it's only when we look to see whether the cat is dead or alive, or whether the electron is here or here or here, that we force the thing into an actual, like, pick one sort of thing. Pick one of the scenarios and be in it. But if we don't do that, then it's like it's in both a dead and alive state. It's in all the different spots of the wave. It's passing through, even though it's one electron, it's passing through both slits. Okay? What does all this mean? It means that we cannot predict or track an electron's path precisely through space and time. We can't. The best that we can get is the probability of where it would be. It leads us to Heisenberg's uncertainty principle, and this I think is, okay, so Heisenberg's uncertainty principle. And what he says is that you can't know everything about an electron within an atom. So he paralleled it to us looking at the moon. So here's the moon orbiting the Earth. We can send a light ray up to the moon. It will strike the moon. It will come back to us, and we'll know this is where the moon is. When that light ray, whether it's a laser beam or whatever it might be, strikes the moon, it doesn't cause the moon to go careening off somewhere. But if this is the nucleus of the atom and this is the electron, and we shine some type of light or something in to strike the electron so that it can bounce off of it and come back and tell us where the electron is, well, when it hits the electron, it makes the electron go like careening off like crazy, totally destroying the orbitals that we're trying to find. Okay? And so there's no way that we can see an electron's motion without destroying the orbitals that we're trying to look at. Okay? And so we say that the electron's motion is changed or altered in a way that can't be avoided or corrected for, like predicted. Okay? And that if the orbitals really were the way Bohr was suggesting, they would be completely broken up by our attempts to verify their existence. So the best that we can hope for is the probability of where the electron would be. Okay? So all of this work with Heisenberg, he was working with Max Born, who suggested the probability. So Heisenberg came up with his uncertainty principle, and avoiding calculus and putting it in what you know, deltas. What he says is, and think of the deltas as like how certain you are in an answer. So like plus or minus. So the smaller you get your plus and minus x to be, so the more exact you know the position, the less you're going to know about the electron's momentum, and therefore that position will change in a way you can't predict. The more you know about its momentum, the less you'll know about where it is. And so it's because these two multiplied together always have to be bigger than Planck's constant divided by 4 pi. So if we make delta x really, really tiny, the change in momentum is going to be huge. Okay, so there's always some uncertainty. So if we know the position of the electron exactly, then the change in momentum will be infinitely large. Sorry about that. Okay, and vice versa. So we can't know everything about an electron's path, and therefore we can't track it through the atom. Okay, so all of this leads us to the quantum mechanical view of the model. Okay, and the quantum mechanical view of the model was proposed, we're going to say somewhere around 1926. Now, the contributions are from a whole bunch of different people. Quantum mechanical view of the atom, I think I was saying model. Okay, and it's called the cloud model. Okay, and so it begins emerging around 1926. Some of it agrees with Bohr. It agrees with Bohr that the electrons can only exist in discrete energy levels, discrete energy states, but no others, okay? So just like Bohr had said they could only be in certain spots, this model says the same thing. They exist only in discrete states of defined energy and no others, and that they can move from one of those states to another by absorbing a photon of energy, and if they fall back down, by emitting it. But instead of there being well-defined circular states, like Bohr said, they don't believe that. They believe these discrete states are more spread out through space, and they're more like clouds. Okay, so the discrete states are not well-defined circular orbits, but rather they're clouds. And just like clouds in the sky, they have different densities, and the higher the density of the cloud, the higher the probability of the electron being there. The lower the density, the lower the probability of the electron being there. Now, these discrete states are no longer called orbits, they're called orbitals. Okay, orbitals. And the size and the shape of the cloud, the orbitals, isn't well defined, okay? It can be calculated using Schrodinger's wave equation, but just like a cloud in the sky, it doesn't have a boundary, a solid boundary. It spreads